Hi everybody, welcome to another video in linear algebra, section 2.1, matrix operations. So this is just a review what we learned back in algebra. Matrix notation, a matrix A, just capital A, is an m by n matrix. That is, so the first number denote the number of rows, and the second number denote the number of columns, and corresponding to a row and a column on particular row and particular column. We say row on the ith row and the j column. There will be an element denote a, I, j. So if we call the matrix is capital A, then the little a is just a scalar meaning just a number on the I row and the j column, and this is called the ij entry of A. So it is on the I row and the j column. And so the index, we see A11 meaning is the first row, second column. I mean first row, first column, and then first row on the j column, first row on the n column, and so on. Unless if we have to go some very high, let's say when we write like this, then we don't know if it is on the first row on the 23rd column or on the 12th row on the 13th column. In that case, we'll put the parentheses there to denote that is going to be on the 12th row and the 3rd column, if we get that much. Right. Each column A is listed of m real numbers. So for example, if we look at the first column here, all of those numbers will change. So the first column, the I column, on the way to the m columns. I'm sorry, the first row, the I row, and the m row. We see the second number denote the columns, all of them on the first column. And here on the row j, all of them are j, first row, second row, and then I row and m rows, and so on. Yeah. So A is the list of m, the columns of A is the list of m real numbers, which is vector in Rm. So they're from 1 to m, so they're m components. Therefore, it's the vector in Rm. The columns are denoted A1, A2 all the way to An. We already seen that earlier. The number ij is the ith entry from the top of the column vector aj. So if we define some particular vectors like a1, aj to an, then we just look up for the I entry from the top. Two matrices are equal if they have the same size, meaning the same number of rows and the same number of columns, and the corresponding entry are equal. So they have the same size, and each number will have to be equal to the corresponding number on the other matrix. Given m by n matrix A, the transpose of A is an n by m. So we transpose from m by n to n by m, meaning the rows become column and the columns become rows. And we denote as A transpose, whose columns are from the corresponding rows of A. So we just switch the rows to the columns. Right. Different type of matrices. The diagonal matrices is an m by n matrix whose the matrix whose entry A11, 2, 2, and so on form the main diagonal of A. I'm sorry, the diagonal entries are the entry on the diagonal. So we can see here, if we have A11 here, A22, and then so on, those will form the diagonal matrix. I'm sorry, diagonal entries. The diagonal matrix is a square matrix whose non-diagonal entries are 0. So we might have, I give just an example for diagonal matrix. Is something like this: 1, 0, 0, 0, -2, 0, 0, 0, and 5. So we have the diagonal entries 1, -2, and 5, and everything else other than the diagonal have to be 0, whose non-diagonal entries are 0. Of course, we still can have 0 on one of those diagonal entry, but other than the diagonal have to be 0. The identity matrix is the diagonal matrix whose diagonal entries are 1. If all of entries on the diagonal are 1, then it is the identity matrix. An m by n matrix whose entries are all 0 is called a 0 matrix. Well, for the 0 matrix, we just say 0 because we have the 0 and the 0 vector and the 0 matrix. Just write 0. There's no special character for that. Right, so there's some terminologies here. The sum of two matrices. If A and B are m by n matrices, meaning they have the same size, then the sum of A and B is the m by n matrix. So A is m by n, B is m by n, and A plus B is also m by n. And the entries on the ij, the ij entry is the sum of the corresponding entries of Aij and Bij. So very simple. We just add or subtract the corresponding entries. If it is subtract, then we subtract. If we add, we just add corresponding entries. If R is a scalar and A is a matrix, then the scalar multiplication R times A is a matrix whose entry R times the corresponding entry of A. So pretty much if we have numbers multiplied to a matrix, we multiply that numbers into every entry of A, every entry of that matrix. Right. So this is pretty basic. So just jump right into the example. Find negative 2b. This is the matrix B. So I have 2 times negative 2 times the matrix B. So simple enough. Just take negative 2 multiplied to every entry of that matrix. So negative 2 times negative 1, 2, 0, negative 4, negative 12, negative 8, negative 8. Right. Of course, if we have a calculator, we need negative 2 first, and then the matrix, 2 rows, 3 columns. 2 rows, yes, 3 columns. Negative 1, 0, 2, 6, 4, 4, and was that straightforward. Next we have A plus 3B. Just switch to a different color here. The matrix A, 1, 3, negative 2, 3, 0, and 1. Plus 3 times the matrix B, negative 1, 0, 2, 6, 4, and 4. Right, so just like normal order of operation, multiply, divide first, but in matrix there's no division, so just multiply and then add or subtract. Now multiply 3 into all of this first. Negative 3, 0, 6, 18, 12, and 12. And then we just add them first with the first, so negative 2, 3, and 4, and 21, 12, and 13. Right? So, just enter exactly as we see it. This 1, 3, negative 2, 3, 0, 1, plus 3, negative 1, 0, 2, 6, 4, and 4. Right. Yeah. Of course, if you use NTI 83 or the calculator, because you have to enter the matrix differently, but this is how we enter the matrix. For example, we can also hit second matrix here, and then we store the matrix in edit 2 by 3. So 1, 3, -2, 3, 0, and 1, right? And then second quick, now I have the matrix A in that. Now just go to B. You have to edit and go down to B and enter the matrix B, also 2 by 3. We have -1. This is negative sign. 0, 2, 6, 4, and 4. Once we're done, second mode, quick. Now we do the same, just type A plus 3B. So we have, so when we go to edit, we input the matrix. When we, under names, we recall it. So highlight here, names, A, just hit enter. And then plus 3, second matrix, 3B. Of course, that does the same thing as we did before. The difference when we enter in the matrix and we enter everything in the home screen is that when we enter the matrix here, we use this arrow to navigate the cell. We don't hit enter in between. When we in this mode, we're going to hit enter to jump between the entries. Right, that's all. Right, to A minus C. Uh, 2 times A minus C. Two times, once again, multiply first. So multiply everything by 2. 2, 6, minus 4, 6, 0, and 2. Subtract 2, -1, 0, and 2, 3, and 4. What we see here is this is a matrix of 2 rows, 3 columns. 3 rows, 2 columns. They don't have the same dimension. So if they don't have the same size, there's no corresponding between them, so we cannot subtract. So in this case, we call this undefined, because of different size. Yeah, they have to have the same size, the same number of rows, the same number of columns. So there will be the corresponding between the matrices. Since we don't have that, it is undefined. Right, next A plus C transpose. So matrix A, 1, 3, -2, 3, 0, and 1, plus C transpose. So the transpose in order of operation, let's say if we have to have something like 3A minus 5C transpose, what we'll do first. So we have to multiply first, then add or subtract. Actually, the transpose is even before that, so we're going to take care of the transpose first, and then we multiply, and then add or subtract. Or if we can treat that almost as a power. Right, now transpose. Transpose means the row becomes a column and the column becomes row. So 2, 0, 3, that's the first column. We can write that as the first row. And second column, turn that into second row. Now we do have the same size matrices, so we can add them. So it will be 3, 3, 1, 3, I'm sorry. 2, 2, and 5. Right. Just enter in calculator so where so I can show you where the transpose is. Right. 1, 3, -2, 3, 0, and 1. And then plus, I'm just going to enter this and then transpose. 3 rows, 2 columns. Right. 2, -1, 0, 2, 3, 4, and then transposes. Second matrix, go to math, and you see on the second one, that is transpose. And that's what we have. Right. Simple enough. So here are some properties of matrices. Again, A plus B is B plus A, that is commutative. R times A plus B is the same as RA times RB, this is distribution. A plus B plus C is the same as A plus B plus C first. So when we have 3 matrices and we add them, it doesn't matter the order we add them, could be the first and second, or the second and third first, it doesn't matter. Also distribution, identity, and another associative. Matrix multiplication, we already do this, but this is just a quick review. If A is an n by n matrix and B is an n by p matrix with columns B1 to BP, then the product of AB is m by p matrix whose columns are AB1, AB2, and ABP. Okay. Or alternatively, we can define a product is the entry in row I and the column J of AB if the sum of the product corresponding to the row of I and the J column. So if we want to multiply, we're going to take the row of I, multiply with, the row I of A, and multiply with the column of B. So the row of A and the column of the second matrix, the row of the first one, the column of the second. Just like the notation, when we write the notation for the matrix, it's row by column. So row from the first matrix, column come from the second matrix, and we write like this. Because we'll do more example. But first, let's just the definition of the size. Let's say A times B. A is m by n, and B is n by p. The middle numbers must be the same, in which case the product is defined and the dimension will be the outside number n by p. Right. And then when we take a row in the first matrix, multiply by the column of the second matrix, and we just keep doing that. Right. Let A be an n by n matrix, and B and C have the size for which indicate sum and product are defined. So we have associative, distributive, and then for all those properties. Just a reminder, IM is the identity matrix of m by n, m by m. So IM identity matrix of m by m. So identity once again is the diagonal matrix. All the entries on the diagonal are 1, 0 everywhere else. So like 1 0 0 0, then 0 1 0 0 0 1, and so on. And m by m, so denote by m, meaning that this will have m rows and m columns. We'll just go all the way to form that identity matrix. Right. Next, if A is a 3 by 5 matrix and B is a 5 by 2, what are the size of AB and BA? Right, if they are defined. So let's just do each of them. We do A times B. A is a 3 by 5 and B is a 5 by 2. Middle numbers do match. So the outside number 3 and 2 is the dimension of the product. Dimension is going to be 3 by 2. Now if we switch the order B times A, B is the 5 by 2, A is the 3 by 5, and this number do not match. So just say no match. So in that case, the product BA is undefined. Right. So middle numbers must be the same. Right. Here's some example here. We have compute A times B, matrix A, matrix B. So let's check the dimension real quick. A is a 2 by 2, 2 rows, 2 column. B, 2 rows, 3 column. So the middle numbers do match. The outside is going to be 2 by 3. So A times B is going to be 2 by 3. Right, so let's write it out. Two and 3, 1 and negative 5, 4, 3, 9, 1, negative, and 4, 2 and 4. Right. Now, without doing anything, we know that 2 by 2 times 2 by 3, the outside number is going to be 2 by 3. So we end up with 2 rows and 3 columns. 2 rows and 3 columns. We're going to get that. Now we just perform the operation. Let's say if we want this one is on the first row, first column. So we use the first row, the row from the first matrix, the columns from the second matrix. And we have 2 times 4 plus 3 times 1. That will be 11, right? Yeah. So row times column. 2 times 4, 8, plus 3, 11. Now let's say if we want this entry, that entry is on the first row and third column. The row comes from the first matrix. The column comes from the second matrix. So since this one, first row, third column, row from the first one, column from the second. 2 times 9 is 18, plus 12, 21. And with that, of course, we can complete this table. I'll try another one. Let's see how about this one. That is on the second row and the second column. So we use second row for the first matrix and second column. 1 times 3, 3, plus 10, 13. And of course with that we can complete the table, the matrix product here. Right, this one, first row, second column, first row, second column. So 6 minus 6. Second row, first column, 4 minus 5. And finally, second row, third column, 9 minus 20. All right, let's check. Two by two. Yeah, just enter everything in the calculator. Right, 11 0, wait, 18 and 12, okay. Yeah, I'm glad I checked, that will be 30. Yeah, 18 and 12, that's 30. 30. Right. So that's all we do. Next, find the entries in the second row of matrix A and B. Matrix A times B, sorry. Should check the dimension. The matrix A is 1, 2, 3, 4 rows and 3 columns. The matrix B, 3 rows and 2 columns. So the product of A times B is going to be 4 by 2, the outside numbers. Since the middle numbers already match, the outside numbers will be the dimension of the product. If the middle number do not match, the product is undefined. Right, so we're going to do that. To -5 and 0. Right, times B. Right, the product is going to be 4 by 2 matrix, so 4 by 2. This question, they want the second row in the product. So we want these two elements, these two entry. So first, to get this entry, this one on the second row, the first column. So second row and the first column. So we have 3 on each box. So the first with the first, second with the second, and the third with the third, and then we add all of them up. -4, just going to say -1 times 4, -4, plus 21 minus 12. Right, so 21 minus 16 is 5. Yeah, and then we want this entry on the second row, second column. So we're going to use second row and the second column. 3 on each, 3 entries in each box. First with the first, second with the second, third with the third. -6 times -1, +6, plus 3 times 1, plus -4 times 2. So that is 9 minus 8, so it's 1. Right. So that's all we have. Of course, we don't need to have do the whole multiplication. Yeah, but just calculations. I'm not even let's not waste time to check the answer with the calculator. Right. So in general, product of A times B is not equal to B times A. Notice that in addition, we have commutative. A times A plus B is the same as B plus A. But we don't have that in multiplication. Case in point, A times B may exist and B times A is undefined, so they certainly do not equal in general. And also the cancellation laws do not hold for the matrix multiplication. That is, if A times B equal to A times C, it's not true in general that B equal to C. So we cannot cancel on both sides. In general, if A times B is equal to 0, we cannot conclude that A is equal to 0 or B is equal to 0. Yeah, let's consider one example. I think we can come up with one. Right, so when we multiply these two together, we have 0. Just do this quickly. Right, so the product is equal to 0, but none of them is equal to a 0 matrix, right? So in general, the product equal to 0 doesn't matter. One does not conclude that one of them has to be 0. This is an example. This is a counter example. Right. Next, the power matrix. If we have A is the n by n matrix. By the way, when we say A n by n matrix, when those numbers are the same number of rows, same number of columns, then we say they are a square matrix. If we have a number k that is the positive integers, then the powers is just multiplied by itself k times. Oh, that's rather obvious. Right, here's some properties. A transpose, and then transpose again, we'll get back to A. The transpose of the sum is the sum of the transpose. R times A transpose is equal to R times A transpose. But the transpose, the product, is the product of transpose, but in the reverse order. Right. So we have some very simple example here, just very minimal example. We have a matrix and then also a matrix, but if we only have one column, we call that is the column matrix, or we just call a vector as we did earlier. Right, A times X and then transpose. So we do inside the parentheses first and then we transpose. Right, so A is the matrix. Times X. What we have, transpose it. Right, so just row times column. 5 times 3, 1 times 5, minus 3 times 3. 1 times 5 is 5, minus 9, 5, minus 9. Negative 2 times 5, negative 10. 4 times 3, 12. Negative 10 plus 12 is 2. And then we transpose this, and we end up with negative 4 and 2. So a column turned into a row. Well, let's check. One, negative 3, negative 2, and 4 times alpha zoom. Only one column here. Right, 5 and 3. And then transpose once again second matrix. Go to second tab. This is where we go to the RIF, which is down here, but the transpose is the second one. Right, that's what we have. Next, X transpose times A transpose. I will write X transpose 5 and 3 transpose, and the matrix A transpose. So I write the transpose first, because we do the transpose before we do the multiplication. So that becomes one column becomes one row. Then the matrix row becomes column, rows becomes column. Because I write -4 for no reason. Right, row times column, row times column. 5 times 1 is 5, minus 9, 5 minus 9, and -10 plus 12, -10 plus 12. And this confirms that A times X transpose is equal to X transpose A. So once again, the product transpose is equal to transpose of the product is equal to the product of the transpose, but in the reverse order. So we can say a X transpose is equal to X transpose times A transpose, sorry. Right. Next, let's do X times X transpose. X is 5, 3. X again. Sorry. X is the column vector 5, 3. And then 5, 3 again, but with transpose. So 5, 3. And then we transpose that 5, 3. So row times column. So this is, if we check the dimension, 2 rows, 1 column, 1 row, 2 column. So we will end up with a 2 by 2 when we multiply this. 5 times 5, 25, 5 times 3, 15, 3 times 5, 15, and 3 times 3, 9. Right, X transpose X. 5, 3, transpose 5, 3. 5, 3 transpose, 1 column turn into 1 row. Now this one we have 1 row, 2 column, and then 2 column and 1 row. Sorry, 1 row, 2 columns, and then 2 rows, 1 column. The middle numbers are the same. We're going to have 1 by 1. So rows times column. 5 times 5 plus 3 times 3. 5 times 5, 25. 3 times 3 is 9, and that will be 34. Right. Even though this is just a matrix of one number, but I'm still use the matrix notation. If a number by itself, I write 34, but this is the matrix of 1 and 3. So just put in the practice. Right, next 5a squared, so a times a, pretty much. I'm just do this by hand and then I check with the calculator. Right, row by column. Row by column, right? Just going to scratch 1 times 1, 3 times 0, 4 times minus 1. So that is 1 minus 4, so minus 3. 1, 0, minus 4. And 1 times 3 is 3. 3 plus 18 and plus 12. That is 30, 33. And then row times last column. 1 times 4 is 4, 3 times 0 is 0, 4 times 2 is 8. So we have 4 and 8. 4 plus 8, 12. Right, now second row, first column, 0, 0, and 0, so that's easy. So times 3, 6 times 6, 36, and 0 times 2 is 0, so 0, 36, and then 0 times 4, 0, 6 times 0, 0, 0 times 2, 0, so all 0, 0, and 0. Negative 1 times 1, just write down. Negative 1 times 1, 3 times 0, 2 times negative 1, so that's negative 3. Row times column, negative 3 plus 18 plus 6, 24 minus 3, and row times column, negative 1 times 4, negative 4, 0 times 3, and 2 times 2. Right. Yeah, notice that when we do the powers, it has to be a square matrix. Yeah, you cannot have 2 times 2 by 3 times 2 by 3. Remember, when we define, it's only for n by n matrix, only apply to a square matrix. Right, so we have 1, 3, 4, 0, 6, 0, negative 1, 3, and 2. We don't even need to multiply by itself, just use power. Of course, if we can square, we can cube. And we can just keep doing that for powers. Right, now, next is an interesting problem. We have the matrix A. How should we compute a square x? So let's just write out. We have a square x. So should we multiply a by a and then a by x? My question is, do we do this first or do we do this first? By the way, x is a vector, so I just write that as a vector. And just put some context, let's say 4 by 4. So x is going to be a vector in R4, so a column of 4 entries. Right, now let's put a dimension and see what works. Of course, let's put all the dimension in. A is a 4 by 4, and then 4 by 4, and then there will be, the vector will be 4 rows, 1 column. It is a column vector. Now, if we multiply this first, 4 by 4 times 4 by 4, middle number match, and we have 4 by 4. And then we multiply 4 by 1, because we end up with 4 by 1, because the middle number match. Now, if we do this first, if we do this first, 4 by 4 times 4 by 1, 4 and 4 middle numbers do match, so this gives us 4 by 1 times 4 by 4, and that gives us 4 by 1. Of course, they should be the same thing. The question is which one is better. Right. Now, notice that in here we do this first, we end up with a 4 by 4 matrix. So how many? We end up with 16 entry that we have to calculate. So here we have to 16 entry to multiply. So here we need 16 entry to be calculated. 16 new entry to be calculated, and then we multiply that to it, and we have this is all entry. We already have this, so 16 entry we need to calculate, and then 4 more entry. So that gives us like 20 entries that we have to calculate, and each one is a row times a column. So a row has 4 entry times a column, so that's a lot of entries. So this is plus 4 entry here, 4 entries to be calculated. Now over here, 4 by 1, there's only 4 entry to be calculated here, 4 new entry to be calculated, and then here there will be 4 new entries, so the total of 8. Right, so of course in that case this will be easier to handle, because when we multiply 4 by 4 times 4 by 1, we still have a column, and then row by column, we don't do that, and the result is still the same thing. So of course that will be better than this one. Alright, now let A be that and B be that matrix. Now multiply them and then compute B transpose A transpose. So simple enough, good practice. So just how good we compute this. Of course we go with this. This is better. Right, A times B. Right, 3 rows, 2 column, 2 rows, 3 column, 3 rows, 2 column, 2 rows, 3 columns. Went up with the 3 by 3. Right, 2 and 0. 1 minus 8 minus 4 minus 10 3 times 2 6 0 times 0 3 times 1 3 and that's 0 3 times negative 4 negative 12 and 0 2 times 2 2 times 1 is 2, and 3 times 4, so 2, and 3 times 4 is 12, so 2 and 12, 14, negative 4, so negative 8, 15, 7. I'll just use the calculator just to confirm what we have here. Three rows, 2 columns. It's -4. Right. Next we can calculate B transpose A transpose. B transpose A transpose. Rows becomes column. Row become column. Column become rows, and row become column. 1, -2, 3, 0, 2, and 3. Right. Multiply 2 times 1 is 2, and that's 0. 2 times 3 6, and then 0. 2 times 2 is 4, and then 0. 1 times 1 is 1, minus 8, 3, and 0. 1 times 2 is 2, and 12, that's 14. -4 times 1, -4, -10, -14, and -12. -4 times 2, -8 plus 15, -8 plus 15, 7, -8 plus 15. Right. Now, what we see here is that A times B this is B transpose times A transpose. Notice that these are the transpose of the others, as you see. Row become column. I'm sorry, columns become row. And that. So in fact, if we take this product, transpose of the product is the product of transpose but in the reverse order. So indeed, this is the transpose of the other matrix. Right. So with that, I stop section 2.1 at this point. As always, and see you in another video in linear algebra.